Welcome back for those of you who have chosen to come in and have a look at the extension question. And there it is on the screen. So a mass on spring system oscillates with a time period of capital T if an identical spring is attached in series with the first. What is the new time period of the system? So as usual, go away, pause the video and have a go at it yourself before you come back for me to go through the answer. So first then, with this problem, what we need to really do first is just remind ourselves about how springs work in series. We will remind ourselves how they work in parallel at the same time. So if we have two springs in series, and as I said, we'll do the parallel version as well, just because we can. Okay, so we'll look in general terms first, K1 and K2 for that one, K1 and K2 for that one. So there is the series version. And there's the parallel version. Now, when it comes to springs, what we've got to remember is that the equations, they look very similar to the same equations when we do combinations of resistors, but they work the other way around. So when they're in parallel, the total spring constant is the sum of the spring constants in the system. So if we had 3 in parallel, K1, K2, K3, it would just be K1 plus K2 plus K3. And then when we're working in series, that's when we use the reciprocal equation. So 1 over the total spring constant will be 1 over K1 plus 1 over K2. So you notice, obviously, when we're doing resistors in series, we add them together, and resistors in parallel, we use the inverse equation. But you can see here that when we're doing springs, we treat the spring constants in the opposite way. So in parallel, we add them together, and in series, we use the reciprocal equation. Now, we've got two identical springs, which of course means that the spring constants are the same. So when we try to calculate the spring constants, 1 over K total is 1 over K plus 1 over K. Now 1 over K plus 1 over K is equal to 2 over K, and therefore when we take the reciprocal of both sides of that equation, we get that the total spring constant is the spring constant of one of the springs divided by 2. Now, in general, if we have n identical springs, and this is now the easy way to work it out, if we have n identical springs, then it's just the spring constant of one of them divided by n, the number of springs that we've got. That will give us the total spring constant. But of course, as I said, that only works when we have identical springs. I can't even spell identical there. Let's try that again. If we have springs with different spring constants, then you do need to go back to the equation, the reciprocal equation, and work it all through. Anyway, let's come back to the question that we've got. Now, what I'm going to do first is I'm just going to define T1, which is this time period here. I'm going to define that as T1 is equal to 2 pi root m over K. I'm then going to define T2, which is now the new time period that we're looking for. And that will be T is equal to 2 pi root of m divided by, and now we need our new spring constant. We need the K over 2. We have divided by, so that 2 will end up on the top, and what we're left with then is T2 is equal to 2 pi root of 2m over K. Now you could leave that at that point if you really wanted to, but we can take this one step further and neaten it up a little bit. And what I'm going to do is I'm basically going to split that square root. So basically I'm going to be taking the square root of 2 out of there and giving it its own term, basically. So we end up with T2 is equal to 2 pi root m over k multiplied by the square root of 2. Now at this point we note that here we have 2 pi root m over k, which we've already defined up here as being T1. And therefore we can write our final answer as T2 is equal to the square root of 2 multiplied by T1. And so in other words, if we add a second identical spring, we're multiplying the original time period by the square root of 2, so multiplied by 1.41. It will therefore have a longer time period. A longer time period makes sense because, of course, what we're doing is we are decreasing the spring constant, and because that's on the bottom of our fraction, we end up increasing the time period. And we've got the scale factor. The scale factor is root 2. So there's your answer. I'll just put a red line under that to show it's the answer. Now, of course, what you might want to do yourself is to go back over this and look at what happens if you have 2 identical springs in parallel with each other and see what happens to the time period there. But I'll leave that for you to do in your own time. So that's it then, there's your answer. As I said before, thank you for coming in and at least having a go at the extension question. And I do, of course, hope that you got something useful out of that.